All right. So, has anybody got questions about any of this stuff or any of the problems? Or? No?
Not right now.
Okay. Well, let me go ahead and jump through to one other thing. I don't even know if I want to turn on the projector, but I guess, well, let me kind of go through one aspect of that is if there's this marker. This is kind of a, well, it'll do. So, and let me see what the limits on the board are. So about right here, let's see my hand, probably, let's see. So that way I'm trying to make sure it's on the stream. Oh, I even got quite a bit of distance up there. So maybe about right there. So let's say you had just a simple problem where somebody is going to throw a football. I can't really make a good, here's the dude throwing a football, and he's going to go down here and say, I'll put my coordinate system on it so that that's when he releases. That's a funny looking drawing. So then we'll say he's very disoriented and he's near the sidelines. So it's 20, I don't know the speeds. I'm gonna say it's a really fast throw. So 150 feet per second, 20, let's make it more like I don't know, maybe 30 yards. And then down here at 30 yards the stands start. And there's a bunch of people heads in the stands there. Turns out this thing is a 4-3-5 slope. So the question is, what position do you need to be up here to catch the ball? So this is similar to a lot of these problems in that essentially some sort of projectile motion happens. Either, there's one problem where the ski slope, person comes off the ski slope and the slope is down here and wants to know where he lands. So essentially it's a straight line connected to a parabolic motion. And that's it.
So for like a problem like that, would we be given the angle or would we be given the...
Yeah, you'd be given the speed, the angle, and then this thing and how far it's away. I just hadn't got to the angle yet.
Oh, okay.
So yeah. So you'd be given all that. But the key is there's a straight line. So there's a makeup of all these, and that is there's a parabolic motion, and then a straight line, or I'll say a landing curve or surface or line. Most of the time it's a line. I've only seen one problem in the book that it was a curve. A golfer, for example, I think there was a golfer who was putting uphill, he was chipping it, he was supposed to land up here. There was a couple things like that. That's a line and parabolic motion in a line. But there was one that had an arc like that. So this had an equation, and then you have your parabolic and wants to know where it lands. So essentially they're all made up of a similar concept in that you got your parabolic motion, which that's supposed to, okay, so you know what that means. So parabolic motion, and then a landing curve or a surface. So let's just do this one so you can see how you can get through this thing in a systematic way that occurs every single time. So I don't really know what a good angle is, so I'll say 30 degrees. Or I could let me make it 45, because then it becomes a little easier to work on the board. So 45 degrees. Okay, so first let's tackle this equation. And then we'll attack this equation. So parabolic motion kind of looks like this, you know. X is equal to x naught plus vx naught and t. Now, the y is equal to y naught plus vy naught t minus the fact that gravity is pulling the thing down. In other words, if you had a total vacuum, the speed in the x direction remains the same. The speed in the y becomes, okay, so it goes up and it reaches the top at this part. The velocity of the y at this point is equal to 0. So up into that point, the velocity is going up, turns and starts going down because gravity. During this part, gravity is slowing it down. And then at this part, from here on, gravity's starting to pull it back down and speed it back up. So the key is, how do we manage these terms? And if you look at this one and this one, you essentially have these terms. And Vy. Now, if you had those four terms, you know, when I'm going to say that, I mean a number that goes there. Then you can just fill out everything. There's nothing left. Okay, well, okay, I'm doing feet per second, so this means you got to have G. That's really 32.2. But that's something that is based upon what coordinate or what unit system you decide to pick. In this case, I already wrote down feet per second. So these two. This is based upon where you put your coordinate. Origin. And so this is like a ruler, okay? So a coordinate system is nothing more than a ruler. I mean, I can put it where the guy released the ball. I can also put it down here, over here. If I put it anywhere else, I make the problem more complicated than it's worth. So just put the coordinate system right there. If you do that, these are pretty easy. Okay, so those are the easiest things to determine. This you'll have to deal with cosines and sines, and you'll have to figure out the x component of that 150. So in other words, I've got 150, right? But it turns out, okay, that doesn't look like 45 degrees. That looks more like 30. I've got photo math, so I can basically pick whatever. Do y'all like 30 or 45? Do you care? I just stick with 45. I'll make it look a little bit more. Okay, so here goes 150. So I've got these two coordinates. It turns out the Vx naught is just nothing more than 150 over square root of 2, which is 150 times the cosine of 45, or sine 150, sine of 45. So, both of these are 45. So you can pick which one you want to do. They all end up being the same thing. But interestingly enough, the y is the same thing. So since I picked 45, I made it simple for myself up here. If it's 30, then of course, you'll know that Vx naught is a little larger than Vy naught if that's 30 degrees. So you'll have to make an adjustment. This would be the 150 times cosine of 30. This would be 150 times sine of the 30. And so you know that's all that trig stuff. But the key was, I've got two numbers now. It just so happens they're the same number. Don't have to be. So now I have all this filled out. So I can just write it like this, okay? 150 over square root of 2 t, that's this one. So I took this one and put it right here. And then I put y is equal to, now I have to remember, that goes away because of this. These two make these two go away. So I'm left with this, y is equal to this, and then the 32.2. Okay, so I got 150 over square root of 2 t, that comes from that, minus 32.2 t squared over 2. So now I've got what appears to me to be the equation of this parabolic thing. There's one issue there, and that issue is, okay, and certain people attack these problems differently. One thing is you can work through and try to do it this way. And I've seen people do it, but these are parametric equations, meaning there is another parameter that is not x nor y that dictates the motion or carving out of that parabola. But since, take a real close look here, since this is the case, this equation showed up like this, and now I've got t is equal to x square root of 2 over 150. So now I can remove this equation, combine these two, such that I get y as a function of x. And how do I do it? I take the t and stick it in here, and I take this t, same t, and stick it right in there. And so if I do that, I'll have 150 over square root of 2 times t, which is essentially square root of 2 over 150 x. And then I got to take this same t and stick it in here. So that one gets a little bit more complicated, 32.2, and I get x square root of 2 over 150 squared over 2. So all I've done is taken the t from this equation, stuck it in here, and then stuck it in there. Now, okay, ordinarily, since it's 45 degrees, this thing becomes, the 150, it becomes x. So what you're saying, or what I guess I'm saying is, if you look at the slope of this line at the instant it's released, the slope is just 1. Okay, so here's what I'm saying. Y prime, which is the same thing as dy dx, is equal to, if I took the derivative of this, I get 1, because you take the derivative of this term. And then up here, I would get, I'm just going to basically write this down, some sort of constant times x. And the constant becomes 2 times this, square root of 2, and all this sort of stuff. But it becomes a constant, because that's just the coefficient. Now if I put in y prime at x equals 0, I get 1. So this has nothing to do with the slope the instant you released it, but the other term does. Now, here's what's funny, and I probably should have done this, and I could have done this, and I probably should have now that I see where I'm at. Let's see the implications of, okay, I got a different color for this reason. See the implications of the angle not being, okay, well. Okay, another color? Hello? Another color? We had a lot of colors in here. We don't have any colors anymore. We can just sort of fake it with the white one. I think this room is not used that much. I was talking to one of the business guys. I think this is like the room where they come steal all the markers. Okay, so let's put a box around it. Implications of, basically, let's do this. I'm going to say theta, right? So if you have an initial shot like that, I'll say V naught, the release velocity, which now is 150, cosine theta, Vy naught, initial release velocity, sine of theta. Now, this is generic. In other words, it covers all of them. Just so happen you put it 45 and you get back what I have. But if you take a look at what happened here, at this particular term, so let's look at what y naught becomes right there. Y naught becomes this, V naught sine of theta times t, of course, minus 32.2 t squared over 2. Okay, but x becomes V naught cosine theta t. And there's nothing else. Now, if I take this term and stick it in here, what you'll see, y will become, so I'm not focused on this, I'm focused on taking the t equaling to the x over, x over V naught cosine of theta. That looks weird because the t looks like it's associated with that. So let me do that. And that makes it look a little better. So now if you look at that, I get V naught sine of theta over V naught cosine of theta times t by inserting this in here. Essentially saying that if I take the derivative, I look at the slope is the x component over the y. So you get back what you should there. Am I making sense? So I mean, you don't really have to do this, but if you see things that are like that, you know. So now that you got this.
So why would we do that?
Why would you do this?
Yeah.
Just the only reason you might do this is to look at it and say, okay, I think I've got my numbers right. So if you look at this first term, in this case it's 1. In this case it'd be generic. You look at it, you should actually get back the slope of that line right there. So it's a kind of a way of checking in your mind. Does it look like that's it? Oh, okay, it is. Go ahead. If it's not, then you may start thinking, oh, wait a minute, that's not the slope there.
So it's just a check.
Yeah, just a check.
Okay.
Yeah, it isn't something that you have to do, but as you're going, you might look at it and say, I have an error. Let me go back and figure out where my error came from. This might be a location, not guaranteed that this is going to be a location. Probably more than likely, the location is associated with your finger on your calculator more than not. So I've kind of found that to be the case. So in our case, we end up with this minus. You know what I'm going to do? I'm going to write this over here, 32.2 times 2 over 2 and 150 squared. And I'm going to see if this, so all I'm trying to do is figure out the coefficient there. I'm going to use this photo map just to find that number. Just let it do it. Oh gosh, okay, so it becomes, okay, 0.00143311 x squared. So I think this is my equation. So he threw the ball pretty fast. If he threw it slower, okay, so if he threw it slower, this number would definitely, these two would be on par. In other words, if you're throwing the ball fast, okay, here's the difference. If you throw the ball fast, it goes way out like this. If you throw the ball slow, it can land. So the fact that I have a really small number means it's going to kind of go up there a little farther than I really wanted it to. But it's too late for me to adjust that now. So I'm kind of stuck. Unless the thing calculated wrong. So 32.2 times 2 over 2, 150 squared. That's what. Yeah. So, I already made it that way, so I got to just stick with it. So, sorry about that. So, now the next question is, okay, so if I go back and look at this, if you don't mind, I'll just erase this. It's on the screen anyway. So I have an equation for line or curve 1, which is this, minus 0.00143 143, 11, and there's probably some extra digits that I should, that's like a mistake there. Okay, so there is the equation of this upside down parabola. So there's my upside down parabola. So now all I got to do is come up with the equation of the second one. Well, it's just y is equal to ax plus b. Now, I don't know how you're used to doing things, but a lot of times the way you were taught and then things are thrown at you a little bit different. So in essence, you know, this is easy enough. It's the slope and it's the rise over the run. So it's just going to be 4/3 x. Now, they'll tell you this is the intercept. And this is true, and so you could go back here and find out where it is, or you could just do this. Okay, hang on. Or you could do this. I know if I put in x equal to 30, I should get y equal to 0. So this spot, just find yourself any old spot, not just any, the easiest spot. Find yourself the easiest spot to work with. So if I put in 0 here, and put in 30 right there, then I get y of 0, 4/3 of 30. Wow, did I get lucky? There's a 30 I put in here, and then there's a 3. That wasn't planned. And then b, so it tells you right off that this is going to be minus 40. So if I put in 0, I'm sorry, if I put in 30, it becomes 40 minus 40, meaning that's that point. So does that make sense? So I just sitting there looking at this. Now I could just move it up one. Now the key is, I mean, this part, this equation, okay, which I labeled over here. This equation always comes from parabolic motion. This equation comes from whatever geometry and weirdness he's given you. Sometimes he'll actually give you, if he has those little curved surfaces in the problems, he usually just gives you the equation. If there's a straight line, like you're landing in the stands, then you're going to have to determine that. You have to say, that's a straight line, let me find out the slope, and then let me find out something to find that extra constant term. Then it becomes this. You just go in here and say, well, I want to find where they cross. Okay, here's one crossing spot. The other crossing spot is back here. And it'll come out of the equation, but you don't care about it. No, that's off the string. So this is where this line crosses with that. So you don't care about that. So all you do is you just take this part and equal to that part. So you say x minus 0.00143111 x squared, that's this part, has got to be equal to 4/3 x minus 40. And you'll solve that for x, and what you'll get is the x coordinate here and the x coordinate back there. So let me kind of arrange it together. So I'll put them on the same side, you know, and I'll try my best to, I will try to make my handwriting nice so I can use that. 14311 x squared. So if I leave that there and draw this over, then it looks like I get minus x over 3. Moving that over, it becomes plus 40, and that's equal to 0. Okay, let me make sure I did it. So here, this part, I just copied it down. This part, I brought 4/3 over, and this is the same thing as 3/3. This became minus when it got drawn over. So I got 3/3 minus 4/3, which gives me minus 1/3. The minus 40 got drawn over, it became plus. And so with that, I'm just sort of there. So let me see if this thing will, okay, So it tells me, oh my God, so it tells me that I got two of them. I got an x1 equaling to minus 320, and I got an x2 equaling to 87.29, say, roughly. So, turns out it's got to be the 87. So you go over here, and this is not to scale, so 87 take away 30, I think gives you 57.29. So it's 57 foot that way up the stance. Of course, that and this is not to scale. I didn't know what it was going to look like anyway, so I had no idea. So, and technically, we should be able to put in. Okay, 4/3 of 87. I'm just going to say 87.3 minus 40. This number should give us about the same as 87.3 minus 0.001431 87.3 squared. So what I'm going to do, use my photomath and write down what that is, and I'll write down what the other one is. It says that is 76.39 for the Y, and this, let's see what this one says. There's a box around it. It'd be interesting what it does with that box. It ignored it. So 76.4. So in fact, this is the Y from this equation. This is the Y from that equation. So essentially, it's up here, 76.4, plus or minus a few digits here. Because that's 0.39, and I already threw away some there. So in fact, this gives me back what it makes sense. Both the equations yield me back, if I put in the 87.29 here, or 87.3, give me back the Y from this equation and the Y from this equation. In other words, the Y from the parabola does equal the Y from the straight line. And that's it. That's all. That's the only new thing in parabolic motion that you get here that you didn't get in physics 1, I guess that's what it was. I tried to think about it. It's general physics or physics 1 or something. I don't know. So does that all make sense? Because that's pretty much it. I mean, again, if there's something different, if there's not a straight line, that's given to you usually, some sort of funny curve. Usually it's going to be quadratic or less. Because if this is quadratic, and you put it in here, and this is quadratic and that's quadratic, you can still use the quadratic equations to solve this. So you'll still have that. If it becomes cubic, you got a problem. And it might not be a bad problem. So that's nothing more than saying, I've got a quadratic, and it's possible that I could have a cubic like that. So I technically could have 3 roots, 3 solutions. Generally, that's not going to be given to you that way. Says that that's cubic. I haven't seen him do anything but parabolic. So here might be your I'll just call it ball. So here's the path of your ball. Here might be the path of the surface. It's possible to get, you can get 2 solutions. But you can actually not get 2 solutions. If this one's arced further down than this one, and it goes off, you'll get a non-real solution. Imagine. Non-real. I'll just say non-real. But then you could have this parabola being very, very flat. And say the parabolic flatness is like that, and this one has more. So you could get 2 solutions here. But if the equation he gives you here sort of bends down and is arced a lot, you might not get another crossing over there on the left side. So that's pretty much it. I don't know. The only difference is the pictures might look different. There's a fireman shooting off, hitting the wall. There's a football. There's a lot of football. There's a golf. There's a ski jumper. So all of those are projectile motions, parabolic projectile motions, landing on a surface, either flat, arc, or some sort of curve, and that's it. So I don't know that spending much more time justifies learning anything more than that. I mean, because then I just confuse the issue. So if you understand that and the sequence that I went through to get it, that's it. There's nothing more to it. So now, on another topic, I'll set this up, but I'm not going to complete it. And that is, so he has the XY coordinates, So you got XY coordinates. But there are a lot of people and a lot of good reasons to use polar coordinates. Spinning mechanisms, things like that. And so, let's see, some sort of conference. Okay, I'm not going to that conference. Okay, so let me just lay this out and not go too far into it, because I don't want to be confusing and do too much at the same time. So I'll just set this thing up and we will come back to this. So if we're good, let me do this. So I'll set this up and we will revisit this Monday. So I'm trying to make what I say more valuable than just a bunch of words. So here's the thing. Polar coordinates, people love polar coordinates, especially if they spin in circles. Or if you're an electrical engineer, they love polar coordinates. Because they have an AC circuit and the AC keeps going over and over and over. So for us in dynamics and for them, it's all the same actually. And people don't get there really needs to be taking all that material and put it together into one. So let's say you had a particle came through here, and you decided, for whatever reason, you wanted to represent it in polar coordinates. It's a vector, right? And the vector goes from here to here. This is a scalar here. This is the distance from here to here. And then they come up with this weird base vector. So, okay, it is true. You do have an I, and you do have a J. But now you got this new base vector, and it, believe it or not, it points straight down here. And then likewise, you need this one. So obviously, as this thing sweeps, okay, let me give you another case that might make better sense. Let's say this is attached to a flywheel, and it's just going in circles here. And so this will be the particle path. Well, if it's the particle path, then that is the tangent line to this particle, meaning the r distance doesn't move out or back, just going in a circle. So that, in fact, would be the tangent to a circular path. That's why we like that one. The reason we like that one is we just draw straight out to it. So it doesn't have to be this. It could be anything. It could be something that goes like this. Say the path goes down to that, like a spiral. It could be a spiral. It could be all sorts of weird crap. So here you got that. So now somebody says, what's the velocity? Well, the velocity is this. It's equal to the change in r with respect to time times ur plus, now here's where the kicker comes, dur dt. This is all I'm going to focus on right now. That is it. I'm not going to go any further than focusing on that. I'm going to look at this vector and say, how does it change with respect to time? This is true, and this is true. This is that, what's it called, chain rule. Once I address that, we're done. And then we'll come back Monday and we'll wrap up with that. So how does this vector change? Well, let's say a few seconds later, R is sitting here, and UR points up. Now, here's the thing. The length of UR and the length of U theta are the same thing as the length of I and the length of J. Otherwise, they wouldn't call them basis vectors. So a basis vector is essentially your finger saying, you need to go 400 yards that way. So, or you need to go 400 yards this way or something like that. So it's just basically the direction you need to go. How far you need to go? Well, just multiply that base vector, be it all, this one, this, and multiply times how far you got to go, and that's the vector. So this would be how far you got to go. This is the direction you go in. Turns out this changes. Now, in the book, he does some sort of weird hieroglyphic drawings, and you look at it, you're thinking, oh my God, I'm sick to my stomach. But let's come back to one very simple drawing. I'm going to take the UR, I'm going to draw it and put it right down here. It's drawn out here, but it is the direction that you go from here to here. It can be put right here. The person can be right here, point his finger and say, go that way. So the fact that it's out here just means that geometrically they're giving you a reason that it should be up there. But it can be put right here just as easily. So here's your UR. Guess what? Here's your I. Your I goes out here. It's this far. Here's your J. Guess what? Your J is a little bit further. So this is of length 1. This is of length 1. And so is that. So if you look at that, okay, stare at it just for a minute. Okay, UR is equal to, it's going to be cosine I plus sine theta J. Now let's take a look at that. Okay, so first let me get rid of all the crap on here and say I've got a vector. It just so happens to be called UR. It just so happens the length of this vector, I'm going to just say it's of length 1. It just happens to be called UR. Here's my I, and here's my J. So if I'm basically looking at this, I'm saying that distance right there is 1 cosine theta. So I didn't put the 1 in here, but I could have. And then the other one over here, nothing more than 1 sine theta. And that's it. So essentially, these vectors which change can be mapped back to the I and the J. And that's exactly what that looks like. Here's what's so funny. Okay, so I'm going to map the U theta. Okay, if UR points this way, U theta points out this way. Happens to be theta here. And guess what this vector looks like? U theta is equal to minus sine of theta I plus plus cosine of theta J. Now let's take a look at that. Okay, this distance, cosine theta, this distance is the sine of theta. So we now have both the UR and both the U theta mapped back to a vector I and a vector J that does not change with respect to time. So now let's look at this term. Okay, so if somebody said d UR dt is equal to the derivative of cosine theta I plus sine theta J over dt. That's easy enough. Take the derivative of cosine, what is that? Isn't that minus the sine? It was last week. So, dur dt is equal to minus sine theta I plus cosine of theta j. Did I do that right? Notice what this is, and notice what that is. They're the same thing. So if you take the derivative of UR with respect to time, you get u theta. What do you think happens if you do this? Derivative of u theta. I said I wasn't going to do this, but I might as well. What do you think you could do if you get that? So I just copy it down. So du theta dt. Okay, I'm just going to copy it down. Minus sine theta I plus cosine theta j. And derivative with respect to time. Okay, help me out. Derivative of sine is cosine, right?
Yeah, it'd be negative cosine.
And then I. Derivative of cosine, isn't that minus the sine? And that is the change in u theta with respect to time. Now, stare at this one and stare at that one. And what you find out is, if I remember this right, it just becomes minus ur. And so this vector changing basically is this way, and this vector changing is that way. Now, we'll use this to derive a set, but we're not doing that part today. That's enough for today. But we'll use those two relationships. The next phase we're going to do is we're going to do, obviously this will be the velocity. Then we'll want to do the acceleration next time too. So we're going to do this will become the velocity, that's what it's called. So we work this out. Then we take the velocity, the derivative of this crap, and we find out what the acceleration is. And then we're going to look at some implications of all of that and things that you probably have known but you didn't think about maybe. Or maybe you thought about it but you just like, yeah, forget it, I'll go on, you know. So this is setting up for polar coordinates, you know. And this happens a lot in electronics, all those other things. So, but that's the key. The key in the book, he basically makes a vector. He says dt and dx, and it's like these things. To me, I don't look at that and say, "Wow, I completely get that." To me, I look at this and I say, "I completely get this because this is math. This is the way it is." To me, you look at geometry and you do stuff like that and you make these assumptions. Are they really assumptions or are they approximations? Well, in this case, they're not assumptions. I mean, this is what it is. So that's it. I guess I'm done. And I've got to go to Cabot in a minute because I volunteered for something and it became larger. So I have to write up on the board that static. I sent him an email that statics and fluids was canceled because I had to go. But so that's pretty much it. I guess I'll turn off the stream.